We're going to talk about atomic theory. Now, the idea of atoms is not new. Around 440 BC in ancient Greece, Democritus suggested that matter was made up of atoms. He used the word atomos. So Aristotle, I guess this is not a place that we get dressed, but Aristotle proposed that there was a continuous model without atoms, and this was held for years and years and years. So it was accepted for nearly 2,000 years. Now let's look at the foundations of modern atomic theory. In 1600, Pierre Gassendi published a work defending atomic theory. And then in 1785, the law of conservation of mass was recorded. So, the law of the conservation of mass simply states that you cannot create nor destroy mass. And experiments were performed where reactions were in an enclosed vessel, and it was found that the total mass of the system remained constant. And this right here is an example of what that vessel looked like. Now, the law of definite proportions states that a compound is always made up of the same relative masses of the element that composes it. And so wherever I find H2O, it will always be two hydrogens and one oxygen. Now, the experiments used to establish the law of definite proportions were characterized by careful measurements that yielded accurate and precise results in a laboratory setting. Dalton's atomic theory of 1803 is the closest to the atomic theory that we use today. Now, remember, a theory is an explanation of a phenomenon. There is evidence to back this up. Now, Dalton proposed that all matter is made up of tiny, indivisible particles called atoms. Another part of his postulate, or another postulate to the theory, was that atoms cannot be created, destroyed, or transformed into other atoms in chemical reactions. This is important in chemical reactions. So we're not talking about nuclear reactions, we're talking about chemical reactions. Now, all atoms of a given element are going to be identical. And then atoms can combine in simple whole number ratios to form compounds. Now, most of these postulates of Dalton's atomic theory are true. All atoms of a given element are identical is not. And we'll talk about that here in just a little while. Now, as we have these chemical reactions that happen, atoms from each compound are rearranged to form new compounds. But we have to realize that no atoms are gained or lost in the process. So this is another example of how mass is conserved. So in this example, we have oxygen gas reacting with hydrogen gas to yield water vapor. So I have two oxygen atoms reacting with two hydrogen atoms, and that will yield water that has two hydrogen and one oxygen. The law of multiple proportions states that when you have two or more elements that combine in different ratios, you have different compounds. So this is an example of nitrogen and oxygen. Notice that we can have nitrogen and oxygen with one nitrogen and one oxygen. Well, if we change that and we now have two oxygens with one nitrogen, we change it to a different compound. NO is going to be very different than NO2, which is also going to be different than N2O. They're all going to have different chemical properties and physical properties. Now, all atoms are made up of different things, and these are known as the subatomic particles. So sub just means smaller. Atomic is just of an atom. So these are the particles that make up the atoms. They're smaller than an atom. Now, in 1897, J.J. Thomson observed the deflection of cathode rays. Cathode rays. And this was from a magnetic and electric fields. So he concluded that the ray consisted of negatively charged subatomic particles, and he named them electrons. So one of the subatomic particles that we have are electrons, and they are negatively charged. So the first model of an atom was called the plum pudding model of an atom. Now, in America, we don't really know what plum pudding is. It is a very popular dish in Europe, specifically England. And this is plum pudding right here. We can kind of equate it to a chocolate chip muffin or a blueberry muffin. Essentially, what it said is there was the positive pudding part. So this entire thing was positive pudding, a positive area of the atom. And then it had the negative electrons just kind of splattered all around the positive pudding area. Now, if electrons are negative and atoms are neutral, then what is the positive in an atom? And so this was the popular plum pudding. It was this positive area. So this was the plum pudding model. Now, Ernest Rutherford in the early 1900s, around 1909, performed his famous gold foil experiment. And what's crazy about this is he designed this experiment to prove the plum pudding model. So this would be an example of what was expected if the plum pudding model of an atom was correct. So he designed this experiment to prove the plum pudding model of an atom. And he anticipated that since the negative electrons were sporadically throughout the positive area of the plum pudding, if you shot these positive alpha rays, so they are positively charged, through an atom, they would all go straight through. So all of the positive alpha rays would travel straight through or directly through the gold foil. Now, this is not what happened. As you can see here, the alpha particles were shot through, and most of them did travel and were detected directly on the opposite side. However, there were some that deflected in different areas. So most of the alpha particles behaved as expected, but some were scattered in varying directions. So because of this, Rutherford concluded that most of the atom, around 99.99999%, is empty space. And that there was a small, very, very dense area in the center of the atom. Now, that area was later called the nucleus. So the nucleus is a very dense, positively charged region in the atom, and it's generally said to be at the center of the atom. So in this diagram, this is showing how most of the rays go straight through because most of the atom is empty space. However, some of them, when those positive things get around the positive nucleus, some of the rays deflect in varying directions. There are two more subatomic particles that are found in the nucleus, and they are the protons and neutrons. So we have a total of three subatomic particles. We have the electrons, which we know are negatively charged, protons, and the neutrons. Now, all atoms are made up of these three subatomic particles, and the number of subatomic particles they have will help define what type of atom you are dealing with. So the charge of an electron is -1. It has a mass relative to a proton or a neutron of 0.0005, 4, 8, 6. And this is in atomic mass units or AMUs. And the symbol for an electron is a lowercase e with a little negative sign. Electrons exist in the empty space. And that empty space is around the nucleus. Now, protons have a +1 charge. And the mass of a proton is 1.0073 AMUs or atomic mass units. And the symbol for a proton is a lowercase p with a little plus symbol. The protons exist in the nucleus. So if an element or an atom is charge neutral, it must mean that they have the same number of protons and electrons. Finally, neutrons are charge neutral. They do not have a charge. They have a mass of 1.0087 AMUs, and they are given the symbol lowercase n with the little not symbol. Neutrons also exist in the nucleus. Now, what I want to point out to you is that the mass of an electron is so small compared to the mass of a proton or a neutron. So when you're looking at the mass of an electron versus the overall mass of an atom, sometimes it can be said to be negligible because it is so small. For example, if I were to get on my scale at home and get my weight, it would be a certain number. If I grabbed a piece of tissue paper, that tissue paper compared to me is so much smaller, so it's not going to register on my scale. It can be said to be negligible. That doesn't mean that the tissue paper doesn't have mass or it isn't matter. It's just so small compared to myself. That's kind of what you can take away with electrons. They're so much smaller than the rest of the atom that they don't really register when you get the mass of them. Now, atomic mass units, or AMU, are defined as 1/12 the mass of carbon atom, and that comes from the fact that it has 6 protons and 6 neutrons. So the atomic mass units, or AMUs, I love that unit. It's probably my favorite. Very creative. Like atomic mass units, I know we will make the units AMU. And these are defined based off of carbon 12, right? And so carbon 12 has 6 protons and 6 neutrons.